This month, our external speaker is Professor Soran from the Portsmouth University. The professor Soran research interest in physical metallurgy and processing. Before he worked at the Swansea University, Cambridge University, Manchester, and also in South Korea. And today's talk is specifically going to talk about the abnormal grain growth in electrical steel, theory and argument, and he will present his latest research. Thank you, Professor Sang, and it's over to you.
I did previously with Sunny Shin when I was in postdoc in South Korea with under the supervision of the late Professor Bruno de Koeman when I was his postdoc in South Korea, and I will cover some of the results on that time, which is opened my eyes about the electrical steel about 15 years ago. And then I will go through a work of my two PhD students, Alina Doom and Dwayne Hawizi. They were my very good PhD student. They both work on electrical steel. So I'm presenting most of the work here based on their PhD thesis where they finished last year. And then Fiona Robinson, she was always our industrial collaborator from Cogent Org, supplying materials, and we have a very fruitful discussion with Fiona. So what I will do today, sorry, next. So just going through the history of electrical steel. Electrical steel relatively is a new alloy. It's not like other alloy we've been using it for many centuries. In fact, the first silicon iron electrical steel was produced in 1905. So at the time they just put a little bit silicon, and they were originally designed to replace iron wrought alloy in transformer. And they noticed it have got much better magnetic property if we put a little bit of silicon. But it wasn't till 1930 was first grain-oriented steel was discovered. And later on, in 1934, when Norman Goss was patented, and I'm showing here the United States patent number here, when it's very nice when you look at that patent, it's actually not much difference from the way they we write the thermo mechanical processing and so on. So what Norman Goss in 1934 patented, and he said, if you have a good combination of a chemical composition and along with thermomechanical processing and proper and suitable heat treatment, then we will give a texture for silicon steel to have a good magnetic property when magnetized along its rolling direction. And after 6 years, or 5 years, in 1939 and 40, then the first commercial Goss grain-oriented electrical steel was produced, and since then it has been widely used in transformer. Now, when it's come, sorry, next. So why silicon and aluminum? Just probably is boring for you guys who are familiar with electrical steel, but it's a good revision for the guy who are not familiar with electrical steel. So why you put aluminum and silicon in electrical steel? Because both of them are increasing the resistivity to reduce the induced current. These two alloying elements are both alpha stabilizer, and they are occupying a substitutional site in the iron alpha unit cell. So they are kicking off one of the iron atom and sitting down in the lattice. So they making solid solution. So they are not making any ordered phase, but they are making disordered solid solution with iron, and they can occupy any of the iron atom within the lattice cells. And that addition of silicon, because it has got a smaller atom size, it will cause the lattice a little bit of contraction. So the lattice parameter will decrease with increasing silicon content. And that's, I'm showing the late Professor de Koeman's equation, where we were using it at the time, how the lattice parameter decrease with increasing silicon content. And the reason is why you add in silicon, because if we substitute iron atom with silicon, iron atom is carry 2.2 Bohr magnitudes of magnetic moment. Silicon and aluminum, they don't carry any. So what's happening, you are reducing the polarization for magnetization of the alloy, and hence you are increasing the resistivity and you are of the alloy to reduce the eddy current in the metal, and that's what prevent the movement of the Bloch wall during magnetization process. Now I'm just showing here, I don't have a pointer in my side. So if you look at the graph here, you will see how by adding silicon content from non-oriented free silicon steel, then you are how the resistivity is increased when you add in more silicon. So this is again one of the equations we use for how much resistivity will increase. So if you use this equation, you'll find out is actually by adding only 3% of silicon, you're increasing the resistivity of the silicon steel fourfold of that of pure iron, and that's important to know. So next. So if that is possible to put more silicon, why you don't put a lot of silicon and aluminum? And the reason is very, very simple, because silicon and aluminum, if you put it in steel, they make the materials brittle, and that causes a lot of trouble and difficulty during iron processing, during the hot rolling and cold rolling, because they are so brittle, they make the alloy so brittle, and it will crack during the thermomechanical processing. That's why we restrict the silicon to be around 3.2, 3.3, not more than that. Otherwise, we cannot process it because it will be very hard. And in addition to that problem, aluminum has not very high affinity to oxygen, and causing extra problem during steel making and continuous annealing. That's why we always keep the aluminum below 0.5. Now, the advantage of aluminum and silicon, they are both ferrite stabilizers. So if you look at the phase diagram of iron and silicon, you will see if you add anything above 2.4 silicon, I'm avoiding that austenite at that part. So if I draw a straight line, anything above that, I'm avoiding the austenite formation, even if I put it above 1200, 1300 degrees Celsius. And that's giving a window of annealing window. And that's very important, because I'm opening the window of heat treatment, and that's very important without transforming the steel to austenite. It remain still, and I can do the heat. That's one of the reasons you can do silicon steel to be heat treated at 1200 degrees Celsius and even more, because you are not facing austenite formation. So if you look at the whenever they give you a chemical composition of silicon steel, it is always different from every single stage is come from the thermomechanical processing and annealing. For example, if I look at the as hot rolled electrical steel chemical composition and compare it to the final product, you will see huge reduction of carbon. And in fact, the carbon should be not minimum, should be absent, but we can't do that practically. That's why still there are some traces there. So why the chemical composition is changing, I will show that in the next slides, if you don't mind, Harry. So here we have how the processing is happening for electrical steel, starting from conventional steel making and casting, and then you go to slab reheating at 1400 at some company, then you go for hot rolling. However, if you click one click, however, this is changed in most of the companies these days, because after the continuous casting, if you let it to cool it down, the steel will crack. And that's why we want to keep it hot and straight away directly connected to the hot rolling mills. And through that, we are reducing the energy because when you cool it down, you need energy to heat it up for the hot rolling. But by the direct connection between continuous casting and hot rolling, you will save energy by this. And also, if you leave the high silicon steel anything above 3 to cool down freely after continuous casting, then it will crack. And to avoid that, most of the company nowadays, including Trojan Orb and Tata Steel in Holland, they directly connect in the continuous casting to hot rolling. So in hot rolling, you're reducing the continuous cast plate to a thickness of 2.3 millimeter, but still the chemical composition is changed. Click, please. So if you look at the, I took all actually most of this, all in this slide, images from Trojan Orb before it's closed down 2 years ago. So if you look at the materials when it's come out from the hot rolling, is shattered and knackered, is so tired, the material, because it's been hot rolled, deformed at very high temperature. That's why you need to go for annealing of hot rolling and slide trimming and descaling. And nowadays they use the shot blasting rather than chemical descaling for environmental reason to annealing it at 1100. So click. Then after that, is ready for hot rolling, for cold rolling. Click. And this you will have, after this side trimming and descaling, you will have a much cleaner, free of oxide steel, and it will be reduced to 0.3 millimeter, which is very, very thin, and normally is in 5 passes, as was Trojan Orb was doing it. Then what we do, after the hot rolling and cold rolling is finished, we don't need carbon anymore. We need the carbon for providing toughness and also the strength of the material to be hot rolled and cold rolled. After that, we don't need carbon. Otherwise, it will cause a lot of trouble for magnetization process. And also, we need clean steel. So what we do, we decarbonize it, as we call it, primary annealing. At this primary annealing, what you do, you do primary annealing at 75 hydrogen, 25 nitrogen, and water vapor as well. So the chemical reaction, I put it there for you. Let me just remove the that it doesn't matter, it doesn't remove on my side. So what you do, you have got some chemical reaction between the carbon and hydrogen, as the one I put it there, but also there is another chemical reaction with the carbon and water vapor, and then the carbon will be taken out. However, in the same time, you nitride in the steel by adding more nitrogen. And why we need that? Because we need to make aluminum nitride precipitate, then it will restrain the grain growth at that time. Then after that, because we don't want abnormal grain growth to happen in the primary annealing. And then the secondary annealing will start, where you have where we anneal it at 1200 degrees Celsius. Still, we are in alpha phase. There is no austenite because of the silicon and aluminium effect. And we leave it at 1200 for nearly 2 weeks in a dry hydrogen. So at that process, during the secondary annealing, not secondary recrystallization, that's the wrong word to use, because recrystallization is already partially or completed during the primary annealing. So this is not secondary recrystallization as faultily named. This is secondary annealing, because the recrystallization is actually happened previously. Now we are doing the grain growth. Now at that stage, the aluminum nitride and magnesium sulfide, it will be dissolved at that temperature, and then the grain boundary will be free from then, and then abnormal grain growth will happen, and then you'll have a very large grain, high purity, because there is no carbon, no aluminum nitride and magnesium sulfide precipitate, and you have got a Goss. Hopefully, you will have a Goss texture to be used at transformer. Okay, next. Oh, so just one point before you go here, and if you look at the image for after the secondary annealing, you will see the electrical steel is really tired. Imagine you are sitting down in a big furnace at 1200 degrees Celsius for 2 weeks. When you come out, you are knackered, right? Steel is the same thing. So when they came out, is actually the shape is not the right shape, and also the sample. That's why they do coating and also thermal flattening to make the steel in a shape before they send it to the customer. Okay, next. So now microstructure revolution, this is the work we did it with Sunmi and the late Professor de Koeman. As we see, the microstructure evolution through the hot rolling and cold rolling is a bit complex, and mainly the surface microstructure is not completely, but very different from the microstructure from the cross section, and that's because of the huge strain and temperature gradient across the cross section, which made, especially at hot rolling condition, you will have a dynamic recrystallization, and some of the grain at the edge or close to the roller, they will recrystallize faster than the one in the middle. So microstructure is very complex, and we have to look at both surface and cross-section when we look at the electrical steel thermomechanical processing. As we go for cold rolling, we will develop alpha fiber and gamma fiber, and then after the secondary annealing, the Goss or probably cube will grow abnormally. And this, as we see it, this is the work by Ali Nadoum, my previous PhD student. And then it will occupy. And if you click next, you will see the entire sheet is just contained of one or two or a few grain, which produce, if you click next, the microstructure or even of the surface contain a very, very large grain of gross grain. That's what we wanted. That's what exactly we wanted. So now if you talk about the tertiary evolution, with the core of our understanding in electrical steel abnormal grain growth is just showing we have to consider the tertiary evolution during the electrical steel processing and annealing. I'm showing ODF 5245 section here. I'm showing gamma fiber and alpha fiber. I'm afraid I don't have the cursor or the pointer to look at this, but if you just, so that's, thank you very much, Herin. So this is gamma fiber and alpha fiber. If you click one more, so during the hot rolling tertia, what's happened when you hot roll it, except the dynamic recrystallization, the most of the if I'm visible in the window, I'm not sure if I'm visible because I can't see myself now. So if I look at the BCC unit cell during the hot rolling, most of the 110, it will be stretched and aligned in a way to be aligned with the rolling direction. So that's why you have alpha fiber during the hot rolling. And if you click next, so if you cold roll it, most of the 111 plane plane direction as well will be aligned along the normal direction. There are so many simulations prove that alpha fiber and gamma fiber are will be generated during cold rolling. However, in simple term, if you have a BCC unit cell, and if you push it under this high strain rate at that low temperature, the 110 or 111 plane, they don't have much choice unless they will align with the 110 aligned with the rolling direction, and 111 direction will be aligned with the normal direction, because basically you're just crashing all the lattice, and they don't have much choice unless to align themselves under that huge strain rate. Now, if you click more, however, there are so many studies conducted in the past decade that by increasing the cold rolling strain rate, you are increasing the intensity of the gamma fiber, which makes sense. So more 111 direction to be aligned to the rolling direction. Now, click next. And if we look at that, this is important to understand the texture evolution during the processing. And the reason is because the texture, especially for the guy who believe in nucleation theory, as I'll talk about it later, these texture, they are not coming from nowhere. They're actually inherited from the deformation texture and so on. So most of the guy who believe in the nucleation texture theory, as I'll talk about it in a bit, they believe, sorry, yeah, they believe anything. Am I fine?
Yeah, we can hear you.
Perfect. Perfect, thank you. I thought somebody asked you a question or something. So, these are a point where I indicated that's is believed to be the nucleation texture from the gamma fiber, and then with further annealing, it will be reoriented or rotated toward the Goss or to the rotated tube or tube in the final annealing. So these texture is very interconnected from the deformation texture to the transformation to the annealing texture. That's why we have to understand the texture evolution during the thermal processing. Next. Now, before I start going through the result we obtained in the past 4 or 5 years, I just want to remind you about the tertiary evolution theories of the occurred during the electrical steel processing to make the distortion and also the easier. So the first theory we depend on, and most of the scientists depend on, and even in industry, is oriented nucleation theory. So these guys, they believe when you cold roll the material, there was huge amount of shear transfer, and transition and deformation band will be occurred, and the Goss with others, or a specific orientation will originate and nucleate more rapidly than other orientation, including Goss. And that will give a preference for the Goss to grow normally later on during the final recrystallization. So these guys, they think is actually the Goss grain is nucleated during this crystallization. So if you click, so we thank you, Heron. If we did that with Sunmi to prove the theory. In fact, it's actually for the recrystallization stage. It makes a lot of sense because we capture some of the Goss grain during the after in cold roll, and then for the initial primary recrystallization stage. And actually this is supporting the theory. When you have got high dislocation density, you can have high Taylor factor, so you will have more stored energy. So the grain like Goss has got less Taylor factor, it will be consume the grain with high Taylor factor. So that's the nucleation starting from having, and that's supporting the theory of the recrystallization stage. And next. The other theory is oriented growth theory. So these guys, they believe these orientation, they were already existed in the early stage of the processing, but they grow abnormally because they have a specific boundary characteristic, which is normally mainly used. There are sigma 5 and sigma 7 are responsible for abnormal grain growth. For example, we captured that growth grain in a nanoscale at a very, very, as you will see, you'll see some pixels of EBSD. And in fact, from our side, we couldn't verify that theory, and it didn't help us to understand the abnormal grain growth at that stage. And there are other people, they think, okay, ignore the CSL boundary, but the boundary like between high and boundary between 20 to 45, they are related to the abnormal grain, and they assume Goss grain are surrounded by high angle grain boundary between 20 to 45, where they have got higher mobility than other one. That's why they grow. So we try to thank you, Heron. We try to validate the theory, and we did a set of experiments for the past 4 years with Ali Nadoum and Dwayne Hawizi. So the first argument, we will try to understand if actually Goss grain has got a preference or size or orientation advantages, as many literature blame that they have grain size and orientation advantages, and we try to understand it if they have this privilege during early stage of normal grain growth. So what we did with the first set of the experiment, we have the primary anneal sample, we anneal it at 1030 degrees Celsius for 10 seconds only to capture very early stage of the grain growth, and then at 1070 degrees Celsius for 8 minutes. Now, what we did, we looked at the 7x7 EBSD mapping, and this is captured like 50,000 grain. And what we did, this temperature is selected below the secondary annealing temperature to capture early stage of abnormal grain growth or abnormal. So what we found out, if we look at the chart, the first chart of the, I'm showing the volume fraction of each of the texture component. For example, Goss in blue, tube in beige, brass in purple, copper in yellow, and so on. And I'm showing the primary annealed one in a dashed bar, the dotted one annealed at 1030, and the plain one annealed at 1070. Now, if you look at it, it's actually the Goss grain. The Goss doesn't have any higher volume fraction of the entire other orientation in the sheet, and I'm counting like 50,000 grain. In fact, a tube has got higher volume fraction than Goss, except the gamma fiber one, which is highest in all three conditions. So Goss grain volume fraction was low, and for some reason is decreased, even decreased with increasing annealing temperature. And we said, so we saw this randomness in the Goss grain size distribution within the sheet. So what we decided, we had the all data of the grain size, and we looked at the histogram of it, and we separated the two main grain size humps or the peaks, and we found out is actually 40 micrometer is a stage where the grain grown more than normal, because the annealing temperature, grain size, primary anneal temperature, grain size was 20 micrometer, right? So anything above 40 we counted as a bit later stage of abnormal grain growth. So what so that's why we separated to understand it even further, and we got the same conclusion. And we didn't find much differences, anything below that, and so on. So we tried to do another set of experiments to find out actually if we can prove that microstructurally. So what we did, we did some quasi in situ, part. So we selected some area not using indenter. It might cause some recrystallization during the indentation, so we used marker. So we have the primary anneal, we did the EBSD, then we anneal it at 1070 for 8 minutes, and exactly the same size. However, we were careful about how much we go further, just in case. We just went by a few micrometers, just in case we're missing some information in between. So when you look at the blue box and the red box here, in fact, we found these Goss grain, they have critical size of over 40 micrometer. And when you look at it after annealing, they disappeared. And then that was above our, it was out of our expectation. We didn't, okay, so the grain advantage doesn't mean much in that early stage of grain growth. And then we found out, for example, in point A, we found some Goss identified by, of course, MATLAB, and then they were still the same, or some of them, as in point B, they appeared without any small grain Goss. Probably we couldn't capture that very small tight grain size by EBSD. So this is a proof point microstructurally and statistically. The grain size and orientation Goss that doesn't have these advantages of grain size and orientation advantages at the very early stage of grain growth. Next. So what we tried to validate the second argument, where we try to understand the effect of the CSL boundary on the growth rates. So what we did, we looked at the all sigma 5 and sigma 7. These are the two main sigmas, or CSL boundary is believed to be responsible for abnormal grain growth. And when you look at the frequency and the volume fraction, in fact, the percentage didn't change significantly after we annealed, and their distribution was rather random. And in fact, for sigma 5 was decreased a little bit, and we didn't understand why this is actually important a factor for the abnormal grain growth, where their distribution is very random. And when we did another set of AFP, we said, okay, this is a very early stage. Let's go for the late stage of grain growth. So we anneal the sample at for 1,000 degrees Celsius for 20 minutes, and then for 1,100 degrees Celsius and we found the same result. Then we try to understand how that happened statistically and microstructurally. So what we did, we took the sample which is annealed at 1,100 degrees Celsius for 20 minutes. We had like 10,000 grain to look at it, and we specified each CSL grain boundary. For example, sigma 3 in green, sigma 5 in blue, sigma 7 in red, and so on, as you will see it in the large map there. And then we took every single orientation within that map, including, for example, Goss in red, as you will see it in the bar, in the volume fraction of the CSL boundary. So we try to understand how much sigma 5, sigma 3, sigma 9 are surrounding the Goss drain with and other orientation. And when you look at the data, we found out actually around these grain are very random, and sigma 7 and sigma 9, which thought to be responsible for abnormal grain growth, were lower than cube, kappa, and rotated cube. Now we didn't verify these claims by others that actually CSL is playing significant effect on the abnormal grain growth, and microstructurally we looked at them and they were randomly surrounded by any of the CSL boundary. And we, from our basic calculation, we found out this actually is not reasonable to suggest a small tiny differences between the grain boundary energy, the differences between sigma 5 and sigma 7 can cause a centimeter or a few millimeter grain growth from that small differences. Then we went back to validate the high-angle grain boundary, as we will see it in the next slide. So here we first of all we look at the volume fraction of the all high-angle grain boundary from 15 to 65, and the graph was perfectly fitted McKenzie plot, and that McKenzie plot was obvious that grain boundary was randomly distributed, ignoring the fact that the small or low angle grain boundary, even below 20, that's different. Let's say this is different distribution, but for high angle it was rather random. Now we did the same thing. We separated all the grain boundary. For example, smaller than 10 degree we highlighted in blue. Between 10 to 20 we highlighted in green. Between 20 and 45, which is the main focus point, we want to understand it here, highlighted in red. And then I identified all the texture component, including cube in red, Goss in green, and we plotted how much or what the volume fraction of each grain boundary are surrounding these individual orientation. And in fact, for and microstructurally and statistically found out that actually between 10 to 20, Goss has got slightly higher than others. When it's come to 20 to 45, Goss was a little bit lower than brass, but it was a little bit higher. We shouldn't make any judgment or conclusion based on that very tiny differences of the volume fraction between 40 to 42. And in fact, one of the criticism about this theory is, well, there are other orientations surrounding by 20 to 40 degree, and why they don't grow up normally then. So there's a lot of criticism, but from our side, we couldn't find a solid conclusion that grain boundary will be responsible for that. So next. Then we try to understand the dislocation, store energy, and Taylor factor. And I think this is more related to the recrystallization process during the primary annealing rather than abnormal grain growth. And if you just click a few times, you will see the cold roll. We anneal it at 850 for 3 minutes, and then 4 minutes, and 5 minutes. And this is how this is showing actually there are we were trying to capture the very early stage of the recrystallization, and we look at it in this way. And okay, that slide is over now. But in fact, we try to understand if ghost grain has got the highest dislocation density. In fact, we couldn't do that. We couldn't find that. Rotated tube was considered to be highest G&D density, as we show it here. However, when you look at the next slide, for calculating the Taylor factor, there is the Goss was kind of equal to rotated tube and a little bit lower than the tube. So that theory of having high dislocation density, which shows high store energy, and then higher Taylor factor, it makes sense during the recrystallization stage, but we couldn't find any evidence that is have any influence during the grain growth. So now we try to develop our own theory about this. And if you click next, then we did some experiment on the effect of the heat flow direction on the abnormal grain growth. And that was the first experiment we did it. We put the sample of primary anneal sample in a furnace, and we directed the heat to be the heat flux direction to be exactly on both directions, not on the top and bottom side, but sides, but rather on the left-hand side and right-hand side. And when we did the analysis after we did EBSG after this, we found that actually abnormal grain growth occurred on both sides, right-hand side and left-hand side, when exposed to the heat flow from both sides. So abnormal grain growth direction was parallel to the heat flow direction. And that was surprising for us, because normally heat is second rank tensor and it's not directional. So what we did, if you click one more, so we did, we got some of the thermal insulator of vermiculite treated silica cloth with fiber fracts. We got it from Fiona Robinson and Trojan Orb at the time. So we covered one side. We covered the right-hand side to be the heat flux will not go to that direction, but the sample was only exposed to the heat flux on the left-hand side, and the evidence was clear. The right-hand side, which was insulated, it was just normal grain growth, and the one was parallel to the heat flux direction was abnormally grain growth. And if we click one more to prove that point again, we did the directional heating and the targeted angle. So we rotated the sample at 45 angle, and we saw how the grain growth is actually going through the 45 angles. And we did a lot of slip trace analysis, as I will show you later, that this heat flux is actually following one of the 6 110 direction. And as you will see on the bottom green one is following 2, and the rest is just following one of the 110 direction. Next. And now one of the things we puzzled and we tried to understand it, there was so many other orientation and there were so many other ghost grain on the edge. Why only 1 or 2 or a few of them grow abnormally? Why not all the ghost grain? And that's what we try to understand, because for that little stage of the nanometer, we have to understand it. For the later stage is understandable, because the thermal conductivity, as in proven in in aluminium and silicon nanomaterials or in copper, the thermal conductivity is increased with grain size. So later on at later stage, the gauze drain will get the advantage of its own orientation and drain size, because the thermal conductivity increase with increasing the drain size. But however, at the very early stage, we think the gauze drain are actually grow along 110 plane and expanded dramatically when it was parallel to the heat flux direction. Now, if you click one more, next slide, we did next. So we did a lot of slip traces analysis. Previous one. Just to make a point on the previous one. So what we did, we now it's clear for us. Next. Now it's very clear that the gross direction was parallel to after we did the slip traces. So the traces I show on the map are the traces, and their perpendicular one are the slip direction, right? And it's clear from that analysis that the gross direction was parallel to the 1 or 2 or the 001 direction, and is parallel to the heat flow. So that is the very early stage of the drain growth. This is what's followed. So the direction was parallel to the heat flow direction. So it's appear, one of the things is appear for us is the temperature is not the only factor for the abnormal drain growth, because there was so many other growth drain around, there was so many other orientation, but they didn't grow abnormally. So that's what we try to understand it from a neutron diffraction experiment we did it, and I'm showing it in the next slide. So what we did, we applied for ICE's neutron diffraction facility in Oxford. After so many rejection, we got some bit time. So what I'm showing here, what we did in situ neutron heat treatment. So we take primary neutron sample, we heat treated in situ using a neutron diffraction from room temperature to 1017 with a heating rate, specified heating rate. Now, the diffraction pattern was obtained every 2 minutes. So this is huge data, like hundreds of diffraction patterns. What I'm showing here, I'm just showing here at the peaks of 110 peaks, 100, and a few peaks at room temperature at 1020, 1040, 1070. Just to show, in fact, below 900, there was little change to show anyway. But what we try to understand, what's happened during that, why gauze drain is actually growing that much. So when you look at the delta D spacing, so this is not the D spacing, I'm showing it in the lower graph. I'm showing the delta D spacing, the variation of the D spacing of the lattice plane. Of course, this is standard and well established that by increasing the temperature, the D spacing elastically will expand. That's understandable. However, the 110 was expanded much more than others, and then followed by 100. This is again understandable from the crystallographic point of view. But that expansion rate or high expansion rate of the 110, it gives us the superiority of 110 D spacing expansion, and that's why we thought that the gauze drain is growing dramatically if the heat flux were applied in the right direction. So if you look at the that's okay. You move to that part, because I wanted to talk about the pitch shifting, but I'll talk about it later. Now we try to understand why that happened. So we did two sets of experiment there. First experiment we did it at if you look at the ODF on high heating rate, we did it one on high heating rate, one on low heating rate. So the ODF I'm showing it at the first row of the ODF is at 50 degrees Celsius per minute, which is high heating rate. You will see actually the alpha star fiber and gamma fiber from the ODF is going till 1070 till dramatically they disappeared and producing weak tube and weak gauze. So we look at the volume fraction of the aluminum nitride peaks, and we analyze it. And when we analyze it from the diffraction peak, we actually we recognize that actually if you using a high heating rate during the annealing time, the aluminum nitride is dissolved very sharply to the point of 1070. It just disappeared completely, and that shows not only the growth but also other orientation to grow abnormally, and that's including rotated tube, and that's including some of the tube, that's why you're getting some growth on rotated tube and tube as well in a very low temperature, tertiary intensity. When you used slower heating rate, for example, I'm showing the low bottom of the ODF, we see actually the tertiary changing after even 10-20 degrees Celsius. And the gamma prime was dissolved, and the alpha star fiber completely disappeared after 1040. And when you look at the volume fraction of the pre-state, which is restricting the grain growth till then, but when they dissolve, they are allowing the abnormal range to happen. We saw the if you're using the low heating rate, it was chosen by gradual dissolve of the pre-state. Then I'm starting from 1030 by 1230. So you are allowing the growth grain to get the advantage of that a few nanoscale for the expansion to go much faster. Okay, so next. So we try to understand this further. We look at the peak shifting and splitting and boarding. So as I stated in a few first slide in my talk today, BCC is when you add silicon, because silicon has got smaller atom size, it will be distorted. It will be slightly shrink. It will be contracted. And that lattice parameter is proven to decrease with increasing parameter and from the increasing silicon content, sorry. So if you look at the peaks, you will see the 110 peaks are shifting, and then you will see some peak broadening and partial peak splitting. And the peak splitting are indication of kind of phase transformation to a lower symmetry. So in fact, the idea is when I'm looking at the silicon steel tube seal, I'm not looking for the highly cubic, high symmetry unit cell. In fact, this is distorted. And that distortion, because caused of the silicon addition in a distorted alpha 5, provided great crystal rapid advantage to have only one or two of the 110 to expand much more than usual. And the heating, it will help us to reach the drain bound to dissolve the pre-state greatly. And that was the main, from our institute experiment, we got it. Next. Now, as a final slide, I want to just talk about the closing theory, what we understand it from assessing the previous theories and also the arguments. And our closing theory, and of course, we published 2 papers and can be found online from our work with Alina Doom and Duin Havizi and Fiona. We published it on our channel, is available online. If anybody wanted, I can send it to them. So what we have to distinguish, and our solid conclusion, we have to distinguish between the early stage of the abnormal brain growth and the late stage of abnormal brain growth. So there are so many brain can on the edge can grow normally, but only growth drain are predominating, and that's related to 2 factors. The addition of silicon is distorting that unique high symmetrical unit cell of BCC structure for iron, and that's causing when that one of the 110 direction, one of the O1 is exposed to the direct heat flux, it will go all the way expanded hugely. And because with increasing the grain size, the thermal expansion or the thermal conductivity increase with increasing grain size. So on that 110 direction, it will reach the drain boundary much faster than other orientation, and it will dissolve the pre-state on the drain boundary before the other drain, and then the gauge drain will get its own orientation and size advantages through abnormally at the later stage of the abnormal drain growth. Okay, so next slide, I'm showing the very cozy in situ from the primary anneal, and we monitored all the secondary anneal after 1110 and how we different of the, and this is what gets us to this conclusion, how the heat flux is helping the 110 plane to reach its drain boundaries to dissolve the pre-state, and then this clear boundary of Gauss is already there. So then the high mobility drain boundary will play its role at later stage of the abnormal drain boundary to expand and consume the rest of the drain in the sheet. Next slide. I think this is my conclusion. So in my conclusion, I can say from our experiment and about more than 5 years, and except my previous years with in 15 years ago, we come to the conclusion gauge-oriented drain do not have size or orientation or grain boundary characteristic advantages during early stage of abnormal drain growth, but rather that all these advantages will come to life at the late stage of the abnormal drain growth, and that's including the drain size advantages, orientation advantages, and 20 to 45 high mobility under drain boundary. And the dislocation accumulation, store energy, tail effect analysis is actually very, very relevant to the recrystallization stage, but you shouldn't find any correlation with the abnormal drain growth stage. And also it's demonstrated that the Gauss abnormal drain growth can be theorized as we discussed now with the distortion of the qubit high symmetry by adding silicon and also the heat flux direction to promote the Gauss abnormal drain growth in the unit cell. And from the in situ trial using neutron diffraction, it was evident that the heating rate has direct influence of the temperature control through retarding and advancing the dislocation of pre-state. And for industrial benefit, we recommended to use low heating rate during secondary annealing to obtain very sharp Gauss temperature to use for transformer. So sorry about, because I think I exceeded my time, and thank you very much for listening and listen to this very long talk. Thank you very much, everybody.
Thank you, sir. Please ask the question directly to Soran and switch on your camera, please. Claire, please.
Thank you very much. I found that a really interesting talk and very nice to take us through each of the stages of the thinking to get to the answers. So thank you very much indeed. I guess my question may be a bit rhetorical, but from everything that you've said and from the indication of the influence of really the thermal characteristics being the dominant ones, can I therefore assume that any inhomogeneity through thickness or compositionally that might be inherited through the process aren't really that important, provided you do your primary recrystallization and have a range of orientations at the surface? Everything else is then just driven by your thermal characteristics. Is that about right?
Well, but we have to be careful when we talk about, I mean, thank you very much, Claire, for that very nice question. It's a very important question, actually. We have to be very careful about when you're talking about the thermal flux, because thermal expansion heat as it is second rank tensor, so it's not directional. So when you are putting a heat under any materials or it should be go equally in all three directions, because it's a second rank tensor and it should be not directional as a heat. But what's happened, what we found out from our neutron diffraction data, the unit cell is not cubical, that is distorted, the unit cell, and that's helping at least one or two of the 110 to have very low symmetry. So this is not very high symmetry anymore by adding more silicon. And when you're occupying each of this, because they are substitutional, so you are shrinking the unit cell. By having that, when you are having a suitable 1,1,0 to be expanded during that, and the heat flux actually, if you direct it in a way, it will help the thermal conductivity to reach the drain boundary for the gross drain much better than the other orientation. In fact, if you look at the 1,1,1 plane and its direction, the direction will be 1,1,0, and that's why we saw the same peak splitting and peak broadening is happen in the cube tertiary component as well, because they are sharing that value with gross drain. So the main point is from our understanding is the symmetry is not high symmetry anymore. And so many researchers are dealing with the silicon steel as a perfect high symmetrical cube, and this is what we understand. That's why we don't take any other ideas about the crystallography except the tertia. Okay, tertia we understand it for so long. If you scratch it, you will get the specific tertia too. But what we try to understand, the heat is actually, the heat flux is very, very critical on the direction, because we saw to help that type of the expansion of the specific plane. That's if I could answer your question.
Okay. Oh, thank you very much indeed.
Thanks a lot, Claire.
Hi, I'm just going to take over from Hiran as he has to leave. So I am just going to take over the questions. Has anyone got any further questions they'd like to ask? Must be my effect. It's all gone very quiet.
Maybe I can ask a different question.
Sure.
In terms of, you've shown this really beautifully by using the different heating from the sides of the sample, where you've got presumably a much wider sample, if you like, to observe the effects. If you, I know we don't, but if you were to consider the silicon steel being even thinner than the 0.3 millimeters, do you think you'd reach a limit where these effects would cease to be effective? You'd then not be able to prefer the Goss grains growing?
In fact, it's a good point, and this question is coming from many decades ago, when it started. When if you have a cold rolled sample, if you strain it more on a higher strain rate, or the reduction rate will increase, of course you are changing the dynamic of the dislocation density and store energy within each individual grain, including Goss. And Goss is not separated from the overall grain in the sheet. And if you are talking about the thickness, then that means I am rolled it much more to have much thinner sheet. And if you do that, you are actually increasing the dislocation density, GND accumulation within that. And Goss grain, same as other orientation, they are not separated from that. So there, from our understanding, their deformation, their slip on the specific slip plane to make able to that 1,1,0 to be directed in a way is play a part. Although, as you said, practically we cannot verify that, because we didn't have, we didn't actually test it if we do it on the. But from a theoretical point of view, I think it will change if you're using different thickness or different bulk high during the cold rolling. I think it's perfectly reasonable to suggest that the size will change. The dynamic of this phenomenon for sure, because the thickness is related to the reduction rate anyway. If I could answer your question, Claire.
Thank you very much.
Thanks a lot.
Super. Jachi, you have a question.
Yes, thanks. Thanks, Professor Soran. I'm Jachi from WMG. I got a question. So your idea of the growth of Goss is because of the distortion, because of the silicon. But my question is that why it doesn't show up the distortion effect during the primary oxidation? I mean, at the early stage. I mean, even at a later stage, if it grows larger, it will have a size effect. No matter which orientation it is, it will more likely to consume the surrounding smaller grains. So your theory, I'm still struggling to understand why the effect of the distortion doesn't show up at the very beginning from the primary stage. Thanks.
Thank you. Thank you for the question. It's an important question, but I think I kind of answered it during my talk, but sorry if I didn't make it clear. Let's be clear, when during the primary recrystallization or primary annealing, we have most of the grain boundary are decorated by aluminum nitride and manganese sulfide, and they are pinning the grain boundary hugely. And one of the reasons we are nitriding the steel during the decarbonization process, we put in a lot of nitrogen to react with aluminum to make this precipitate on the grain boundary to not let that grow abnormally at the primary annealing. So it's not reasonable for me to imagine if I have all this grain boundary and I'm creating it during the primary region for the growth drain, or any other drain will grow abnormally at that stage. And bear in mind, during the primary annealing, the grain will grow, but they don't grow abnormally. For example, from our evidence, we showed that if you have 20, probably some grain will reach 40 micron, but not more, because the entire grain boundary are pinned with the grain boundary. Now your question is a very good question. Why there is no other orientation? Well, the only reason we should think about this is actually there is only one lattice plane, which is 110 in the direction of 110, can have that huge lattice expansion as we show it and we prove it in the neutron diffraction data. So what we have that lattice plane, which is basically, to be very honest, this is proved in aluminum and silicon and steel, and for some reason we don't pay attention to that in steel industry. But the 110 is expanding much higher elastically than other plane, and that with that distortion of silicon, it made that specific plane, from our simple calculation, that actually one or two of the 110 plane can have this advantage to expand much more superior to another grain than any other orientation. However, having said that, I still think the cube has got a possibility to do the same, but not in the same extent, and that's need further experiment, to be honest, to see what the difference between the Goss and cube, and why this in our experiment, I mean, is very, very reasonable to suggest cube grain should grow abnormally as well, comparing, but why crystallographically we couldn't reach that point to make this difference. But experimentally, most of the abnormal grain grows with Goss rather than cube. If I could answer your question.
Yes, thank you. Thanks.
Thank you very much.
Mo, you have a question.
Yes, thanks for the presentation. It was very interesting. It was something that I didn't know. My question is, would you think that the silicon content would have an effect on your Goss volume fraction? Because you mentioned that by adding 3% of silicon, that you would have a lattice distortion. Would you, by adding more silicon, have a impact on this effect?
Absolutely, it's a good question, and absolutely, by adding more silicon, it will change. Because this was a proof of concept study. We did it throughout my two self-funded PhD students, so I was free to do it without industrial restriction. But that was mainly proof of concept. So of course, we just assumed this is 3.2. If we did the same experiment, on 3.4, or by additive manufacturing to increase it to 6%, as nowadays they do, you will have completely kind of distortion of the unit cell. And I cannot predict what the difference and what the consequences will be. But the distortion is starting by adding silicon. because of the atomic size differences. And when you are distorting that, then by adding more, for example, the one we expect from that, we are occupying only two of the iron atom in the unit cell. Imagine if you put 6% of silicon, how many iron atom it will be replaced by silicon. And that's further distorting the symmetry of the unit cell, and that's further unpredictable things. And I think one of the things we miss in the physical metallurgy, I'm a physical metallurgist, but one of the things I really miss, we always don't read the nanotechnology and the nanoparticle, and we get a lot of advantage because they do it in much smaller scale about what's happened there, and we always ignore it because we care about the industrial application there. But to answer your question, definitely the point we made, it was a proof of concept. We found this, and I think you are absolutely right. Putting less or more of silicon, it will change that mechanism for sure.
Thank you. Thanks very much. I have another question.
Sure.
So, with regarding your green morphology.
Yes. Yes.
You there, Mo? I think. Are you there, Mo?
Hello.
Hi, you're here. Here again. Sorry.
Yeah, sorry. So I was thinking, would your green morphology also have an impact on your volume fraction? Because I remember from one of your EBSD image that you have a very elongated grain, and it seems that a very flat surface would going along the rolling direction seems it would facilitate the Goss texture formation, or goes against yeah, that's my question. Would it have an effect as well?
Is a good question, and I don't know the answer of that, because normally the elongated grain in the hot rolled one, we look at it as a cross section. When you look at the surface, is all equiaxed. There is no difference. But when you look at the cross section, of course, looking at the cross section will be different because you have a huge strain and temperature gradient across the cross section. So that one doesn't reach. So also, the animalization is happening on the surface, is not happening on the core of the sample. However, based on our finding, the morphology from the surface we look at it is all equiaxed. And if I'm saying that the cross section or these elongated grain have brought effect, we cannot prove that, because that elongated grain appeared as hot rolled. When you cold roll the material, it will be completely the sheet on the cross section. It will transform to alpha fiber, and gamma fiber. And that's why you saw on the cold rolling either very large deformation band. So they will transform to alpha fiber and gamma fiber. These elongated grain, after the cold rolling, they will disappear, because most of the unit cell, they will be crushed till away there 110, it will be parallel to the normal direction. So that image in your mind, sorry, I cannot go back to the question. This is from hot rolling, and that microstructure, it will already eliminated in the cold rolling. Cold rolling microstructure is very complex, and these nice equiaxed grain, it doesn't exist anymore. So when you do the primary annealing after the cold rolling, so ignore the one you just saw, because that's from the hot rolling, that's already disappeared. But after the cold rolling, you do the primary annealing. Wherever we witnessed, it was equiaxed, nice, and the thickness is already 0.3 millimeter. So we didn't expect that to have these elongated grain and different morphology within the surface or the cross section, because the thickness is already, you will see that on the 2.3 millimeter thickness. But when you come to the cold rolling, it's already 0.3. I personally don't expect that morphology will exist before the annealing after that. But did we look at the cross section? No. Otherwise, I don't think it will be the case.
Thank you. Yeah, I'm just thinking if you manage to retain these elongated grains till the cold rolling, I know it doesn't exist. If we manage to have a very flat grain boundaries, would that facilitate Goss formation, or would it go against?
Well, practically, it's kind of impossible. After cold rolling, you will have these kind of grain as they are, because you are reducing it over 75 reduction or 85 reduction. In industrial stage, you'll go sometimes above 90% reduction after cold rolling. But it practically doesn't exist. If, as you said, is an assumption, if even it exists, that morphology will affect the abnormal grain growth, I don't know.
Okay. Yeah, thank you. Thanks very much. I'm just very curious. Thank you.
For me, there are some people, many people, as you know, guys, either you go for crystallography or the microstructure morphology. I'm a guy going for crystallography. I think for me, if I understand the texture, I can understand the microstructure. Some other guy, they say no. Is actually, if I understand the microstructure, I will understand the texture. But for me, is another way. So I don't know. I might be right or wrong. I don't know about that.
Yeah, thank you. It's a very thorough explanation. Thank you.
Thank you very much. Thank you.
Okay, so thank you very much. I think due to time, we will stop it there. I'd like to say a huge thank you to Soran for such a great presentation and for such in-depth responses to the questions as well. So thank you very much, and we will see you at, our guys at the next colloquium. We may not see you, Soran, obviously, and enjoy the rest of your Monday, and we'll speak to you soon. Thank you.
Thank you very much for your invitation. Thank you very much, guys. Thank you.
Bye-bye.
Thank you very much indeed.
Thank you. Bye-bye. Take care. Have a good evening.